Hello guys, in today's lesson we're going to talk about the half-time, lifetime, and decay time, and it's the continue of the chemical kinetics that we have. So let's just start by what is half-time. Half-time is from the integrated rate laws that we did, like we explained, we showed from that integrated rate law the relationship between the concentration of the reactant and time. And three concepts derived from those relationships. One of them was half-time. So what is half-time? We simply show half-time as T half. And what it means is that the time that it takes for the concentration of the reaction to drop to half of its initial value. And if I want to put it in a formula, it would be the concentration of A at time interval T is equal to the half of the initial concentration at time 0. So what is lifetime? Lifetime is basically a similar thing, but the difference is for the half-time, we said the concentration of reaction dropped to the 1/2 of its initial value. But here for the lifetime, it's 1/E, and E is Euler's number, and it means that the time it takes for the concentration of the reaction to drop to 1/E of its initial value. And we show it as a little t here, lifetime. Little t, and so it means that the concentration of A at the given time of t is equal to the 1/E times to the initial concentration. And you guys probably know that E is equal to almost 2.7. So now, half-time of a first-order reaction. Let's talk about that one. So the integrated rate law for the first-order reaction was the natural ln of A at time interval of t minus ln of A at time interval 0. The difference between them is equal to the negative k times t. And so if we can simply change it with using the properties of the natural logarithm function and make it like the ln of concentration of A time interval t divided by concentration of A divided by time interval of 0 is equal to the negative k t. And for the half-time, the integrated rate law becomes, so when we are looking at the half-time, the t here is t half, and our concentration is half. So basically, the ln of I'm rewriting it here. The ln of concentration of A over at time interval t will become like the relationship between the half-time, the concentration and the half-time will be so basically what I'm trying to say is that the concentration of A, the time interval of t in a half-time would be half of the initial concentration, right? So we can just simply write it down like this, or the initial concentration equals to the negative k, and the t is, since it's a half-time, the t is t half. So our equation would be ln half equals to negative k t half. And so now you can simplify and try to t half alone, because you mostly ask for the half of it, half-time. And so t half would be so you just need to calculate divide the ln of half by negative k, and the ln of, so you make the t half alone, half-time alone, and the ln half over negative k will make it negative 0.693 over negative k, or 0.693 over K equals to the T half and halftime. That's how you can find the halftime for a first order reaction. For the lifetime of the first order reaction, you can just simply memorize it, and it's our little t equals to the ln e over negative k, and since you guys know ln is log with e base, so e log e with a base of e is equal to 1, so it's negative 1 over k. For the first order reaction, the halftime is independent of the initial reaction concentration, and each successive halftime is an equal period of time. So now we talked about the halftime of a first order reaction. So now what is the halftime of a second order reaction? For the second order reaction, we again go for the integrated rate law for second order. If you guys remember, the integrated rate law for second order was 1 over the concentration of A at time intervals t equals to the kt with a positive, like for second order was only one that we talked about with a positive slope, positive k slope, plus 1 over initial concentration of A at time interval of 0. And so how do we calculate it? So again, using the relations that we have, so the concentration of A at time interval of t equals to half of the initial concentration, and our t is half. So the halftime would be, this one is half initial concentration, the 2 goes up, so it would be 2 over equals to the k t half plus 1 over initial concentration. And if you make it alone, the t and half, t half, so the t half would be 1 over k initial concentration. That's the halftime of a second order reaction. For second order reaction, the halftime is dependent on the initial concentration, because you guys can see the concentration here is in the formula, but here it's independent of the concentration. You cannot see the concentration of A here because you don't. So simply, you do not need the concentration to find the halftime of the first order reaction. But for a second order reaction, you need that because it's what in your formula, and you have to have that in order to calculate it. And each successive halftime is twice as long as the preceding one. So if you guys remember, for the first order, each successive halftime is an equal period of time, but in a second order reaction, it's twice as long as the preceding one. So what is the half-life of a zeroth order reaction? Again, recall the integrated rate law for the zeroth order reaction. It was the concentration of A at time interval t equals to the negative kt plus the initial concentration of A. And now we have A, which is equal to the at time interval t, which is equal to the half concentration. I can just write it like this: the initial concentration of A at time interval 0 over 2 is equal to the negative k t half plus initial concentration of A. So simply, if you make t alone, the t half would be initial concentration of A over 2k. So that's the half-life of a zeroth order reaction. So if I want to give you guys a summary of what we talked about, so if we want to say, okay, this is our order and this is our half-life expression. Zeroth order, first order, and second order. Or half-life expression would be T half equals to the initial concentration of A over 2k. For the first order, if you guys remember, it's independent of the concentration, and T half equals to the K 0.693, and T half for a second order is dependent on the concentration, K A initial 0. So I will give you guys an example, and I hope you just stop, pause the video, try to solve it, and then continue the video and see if you were right or wrong. I hope you guys have paused the video and tried to solve it. So now we go over the question. It says the first order decomposition of N2O5 into NO2 and O2 has a half-life of 120 seconds. If the initial concentration of N2O5 is 0.85 molar, what is the concentration after 5 minutes? That's an easy question. So you have time. So you know you have to use the integrated rate law, and yeah, that's it. Basically, that's it. You have to have time too. So you can just put in the formula, find the K, and that's it. So solving it, we have the half-life. We have the half-life expression. And since we know it's the first order, we know it's independent of the concentration. So it's 0.693 over K. What is our half-life? It's 120 seconds. So 120 seconds equals to 0.693 over K. So what is K now? K is K will be 5.776. 6 times to the power of 10 with the power of -3. And that will be our expression for K. And now, it says, what is the concentration after 5 minutes? We know it's a first order reaction. So we have to use the formula for the first order reaction. And since we have time, we have to use the integrated rate law. So the integrated rate law for the first order reaction is ln N2O5 to 5 time interval t equals to -kt plus ln N2O5 0. Our time, so we have our half time in seconds, and so on. So we just have to, and our K in seconds, because our half-life was seconds, so our K will be in seconds inverse. So for our T, we have to convert it into seconds too, or we can just simply try to convert this one into the minutes, which I don't recommend it because 5 minutes is just 300. You just have to multiply your minutes, T. We have 5 minutes, times to the 6, since each minute is 60 seconds, and the answer will be 300 seconds. Putting your values in the formula, the natural logarithm of N2O5 at time interval of t equals to the negative. What is our K? It's 5.776 times to the power of -3 seconds inverse multiplied by 300 plus ln of, it says, and now we need the initial concentration. Initial concentration is 0.85. Ln of 0.85 molar. So using this, I guess you guys know how you should calculate the ln. And what you basically need to do, if you calculate this whole number, it would give you an expression of ln N2O5 t equals to the -1.9. So it's a bit of calculus and mathematics, but when you want to find the natural logarithm, like for example, natural logarithm of something is equal to 2. how you should solve it, it's you just simply say that e with the power of that expression. So what we here now have is e with the power of ln into 0.5 equals, at time interval t, equals to e with the power of negative 1.9. And why do we do that? There's a general rule in calculus in which that it says e with the power of log e, which is similar to ln of something. For example, here we have n, for example. These cancel each other's out, and that one goes back of the e, so it multiplies by that. So this one is basically 1. When we say e with the power of ln is log e, so e log e n equals to n, because the n goes back at the back of the e, and it's multiplied by that, and n will be times multiply by 1, and n is basically n. So this is why we do, and then we get we say, okay, we have the ln, we have the number, our value here, so we just have to say e with the power of that equals to the e with the power of that. So we could cancel each other the ln out, and so basically if we do that, this will give us a value, and this also will give us just the N2O5 concentration. So the N2O5 concentration at time interval t will be equal to the e with the power of negative 1.9, which will be 0.15 molar. And I want you guys to think about it. After 5 minutes, we have 0.15 molar. And is it less or more than our initial concentration? It is obviously less than that. But so we know that we're correct by now. What about its halftime? It said by after 120 seconds, which means after 2 minutes, it reaches its halftime, right? And so what does halftime mean? Halftime means we have the half of the initial concentration. And what is the half of the initial concentration of 0.85 is 0.425. So after 2 minutes, we lost 0.425 of molar of our initial concentration. And here, after 5 minutes, we are left with 0.15 molar. And we can conclude that our answer is logically correct. And we can just check it. If is it more than 0.425? So if it's more than that, then there must be something wrong with our calculation, because it shouldn't. And now we get to the concept of decay time. Decay time, it's a general way to describe of the rate of chemical reaction. And for example, it says how long does it take for 90% of the reactant to react? And so it would be like if 90% of a reactant has reacted, then only 10% of it has left. So for example, I will write it down. Okay, we say the 90% of our delta A initial has been consumed, and only 10% is left. 100% minus 90% is only 10% has left. So our delta concentration of A at time interval t is equal to the 1/10 of our initial concentration, and that's it. But for the first order reaction, only the decay time and halftime do not depend on the value of the initial concentration, and it's only in the first order reaction. Now guys, I will give you guys an example, and I hope you just try to solve it and give your answer for it, then check it with my answer. So now you can pause the video and try to solve it and check your answer with mine. Again, if you have any other question, you can comment it on my video and I would happily answer that. So let's get back to our topic. It says carbon-14 is a radioactive isotope with a half-life of 5,730 years. If a particular sample has decayed so that it has only 40% of its original amount of carbon-14, how old it is? So it's a decay time example. So first, we need to find our rate constant. And how do we do it? If we say, okay, after 5,730 years, it's in year, and our, sorry, it's not working, 0.693 over k. And that's how we find our k, which will be it will be 1.21 times to the 10 to the power of 4 year, -1 here. And now we can determine its age using the integrated rate law for the first order reaction. It's ln AT over the initial concentration of A time interval 0 equals to negative KT. We just simply put our value on it. So because it says only 40% of the initial amount has left. So ln 0.4 over 1 equals to the negative 1.21 to the 10th to the power of negative 4t. And our t will be will be 7.57 times to the 10 to the power 3 year. So now let's get another example. So you can pause the video now and try to solve it and then check your answer with mine. So it says a certain first order reaction is 45% complete in 65 seconds. Determine the rate constant and half-life of this process. So since we have time here, we use the integrated rate law for the first order, which is ln A concentration over T equals to negative KT plus ln initial concentration of A. 0, we can rewrite it as ln concentration of AT over initial concentration of A, A0, and equals to negative KT. Okay, so we want our rate constant. And it says 45% is complete, so it means that 55% has remained, which will give us the total value of ln 0.55 over equals to negative KT. And now we can divide this by T and this one by T, which will makes negative K alone and gives the total answer of ln 0.55 equals to over 65 gives us our negative K. The K here would be, I have calculated already, so and I found 9.6 times to the 10 to the power of negative 3 seconds inverse. And it wants, other than the rate constant, a half-life for this. So the half-life of a first order reaction is T half. It's independent of the concentration. It's T half 0.693 over our rate constant, which is 9.6 times to the 10 with the power of negative 3. And also calculate this, which will give us the answer of 75 seconds. It's our half-life. I hope you guys have learned something from me. And again, if you have any problem with it, you just can comment in and I would answer it, and I will give you my contact info. You can text me and I would definitely try to explain it more. Thank you for watching. Please like and subscribe.